This meeting is being recorded.
Program. So I'm excited to tell you about what we have to offer. So today I'm going to probably chat for about 30 minutes or so about the degree programs that we have, namely within structural engineering mechanics, our thesis and non-thesis program. I'm going to talk about our courses. I'm going to talk about some of the research that we do, and then talk about why we think we have a lot to offer. And then again, as Eric just mentioned, we'll take questions and try to answer them at the end. So, first of all, where are we? Well, within the University of Washington, we live in the College of Engineering. So they're on the left. That's us, Civil and Environmental Engineering. I like to show this because, especially in structural engineering mechanics, we connect with a lot of these other departments as well. We do research with folks in these other departments, our students take classes in these other departments. There's a lot of structural engineering being done in aeronautics and astronautics, in mechanical engineering and material science. So there's a lot of opportunities even beyond our department. I'll get to a bit more of that later. Within civil and environmental engineering, our department, this is us. There's 6 groups. We're down there in the bottom in the middle, structural engineering mechanics. And even here, our students will take classes within construction, within environmental, within geotechnical. There's a lot of opportunities to become an expert in structural engineering mechanics with good connections to other aspects of civil engineering. Our department is quite competitive. We're often ranked from, depending on the year, from 12th to 17th. So we're a very well-known program within the country, especially on the West Coast. In the sense of earthquake engineering, we do a really good job training our students and placing them in good places, in good jobs. So this is sort of a typical number, 120 graduate students that we may bring in, anywhere from 100 to 120 graduate students. Our group this year in structures, we have brought in 45, so we're a pretty big part of the department. Those numbers below are actually a little bit outdated. The structures one is current, but the other ones are a little bit outdated, but this is a pretty typical sort of number. So if you come here, you'll have a lot of fellow students that you'd be working with. And one thing I forgot to mention there, I think in the application you would apply to, within civil engineering, to the SEM program, structural engineering mechanics. Of course, you're interested in the program. So within structural engineering mechanics, this is the folks that work here. This is us. So I'll walk through a little bit about what we do, the research projects, the type of work that the different faculty are working on. Starting with Professor Berman up in the top left corner. We often call him a steel guy, but that was what his initial training was in, but he's broadened into a lot of different areas. He has done a lot of work on timber construction, especially in the Pacific Northwest. We're very interested in getting more out of our timber structures. Why not have taller timber structures? Another thing he's working on is rapid reconnaissance of post-disaster scenarios. For example, he was just barely out in Florida with drones flying over and taking pictures and getting a complete map of what the damage is like after the hurricane, so that you can change the way we do design, so you can identify things that we can improve and things like that. Next is Professor Calvi. He's also, we might call him our concrete guy, but likewise, and this will be a common theme throughout the department, he's expanded into several other areas. He does a lot of research on base isolation in seismic zones. He does work on forensic engineering, identifying the damage state of structures based on what they look like. For example, looking at cracks and determining what that means in terms of how safe a structure is. He's got a really exciting new piece of equipment, a panel tester. So we can, if you've taken a mechanics and materials class and you've studied about Mohr circle, we can basically do real world Mohr circles. We can test any stress state that we like based on that new equipment. He's also done some work in masonry structures as well. And then Professor Eberhard, he's also a concrete guy, but he's broadened out into a lot of other areas where structural engineers meet kind of society at large. So he spent a lot of time connecting what we do and how we can make society safer, talking to city planners, talking to departments of transportation, researchers, identifying types of structures that are vulnerable to the seismic threats we have here in the Pacific Northwest and in other seismic zones around the world. Next is Professor Lehman. She's also done a lot of research in reinforced concrete, also in composite concrete steel structures. Likewise, she's done a lot of other areas of research. An interesting one is vertical tsunami evacuation structures. So if there's a tsunami coming in and you want to get out of the way quickly, there's a lot of work being done on tall structures where you can climb up to the top and be safe from the tsunami. The building is designed to withstand those. She's done a pretty broad spectrum of research from the fundamental mechanics in the lab, also numerical computational studies, and all the way through to design, changing the way design code works. Professor Laura Lowe's is now our chair, so she won't have as much time to do as much research, but she's still active. Her background's in constitutive theory, a lot of computational numerical modeling. Peter McKenzie has a strong background in computational mechanics, stability methods, timber. He's actually doing a research project now on identifying, on modeling cracks in rocks based on solar cycles. So every time the sun goes up and down, it creates thermal strains in rocks, and then it goes down and they just change again. After a while, you get heat damage. So he's got a background in computational mechanics, and he ends up doing something very integrated with geotechnical engineers. And I think that's something our department does really well, is this interdisciplinary research. Professor Greg Miller, who is also more on the administration side now, he's a vice dean in the College of Engineering, but he has a background in numerical methods, computational mechanics, software, and especially on the side of making hard mechanics problems approachable with software. Professor Motley, along with me, probably Professor Motley and me are a little bit more on the non-traditional side of structures. So he has done a lot of work on fluid loading of structures, tsunami loading of structures, propellers, hydrokinetic marine turbines. That means underwater energy harvesting turbines. So you might not think these are structures. They're not buildings, they're not bridges, but they are structures. They're mechanical systems that carry loads. That's sort of the mechanics part in the name of our group. Professor Roeder has retired, so he's not teaching classes, but he's still hard to get out of the building. He still comes and does a lot of research here in the department. He's a renowned expert in steel. His name is all over the steel design code. And likewise, Professor Stanton is a renowned expert in reinforced concrete, in pre-stressed concrete. He's also worked in steel, stability, buckling, you name it, he's very interested in that topic. He does a lot of both analysis and lab work. And last but not least, hopefully, is me on the bottom right. My area of research all of my degrees are in civil engineering, but my research is more oriented toward aerospace structures. So I've done a lot of research that's more oriented toward Air Force Office of Scientific Research and things of that nature. But there's a lot of, and I'm very excited to be back in a civil engineering department. There's a lot of really nice opportunities to use that stuff in civil engineering and vice versa. Okay, so on to our program. These are the main two options we have, the non-thesis program and the research program. In the non-thesis program, you would take more coursework, and in the research program, some of those course credits, and we'll get to those details, are replaced with thesis credits. One thing we really don't want to do is have these as two separate, kind of a first class and a second class program. That's not what we intend at all. We want great students in both of these. So it is possible to switch. I've had a number of students who entered as a non-thesis student and switched to a thesis later. And oftentimes we have students who we really would like to recruit for a thesis. They're really good students, and yet they want to take courses, they want to get out, make money quickly. So we're hoping to recruit great students on both ends of this. And I will get to a few more details on those two programs. So in our master's degree program, you have the flexibility to select a lot of electives, but I'll go through kind of the two general routes we have. The general program requirements are 3 required fundamental courses. I'll list them specifically and talk about them later. Then you have to take 4 graduate, meaning 500 level structural engineering electives, and 3 credits of structure seminar. So 3 credits of seminar is approximately equivalent to 1 course. Alternatively, you can take 5 electives and no seminar credits if you'd rather take more coursework and not take a seminar. The seminars are 1 credit each quarter, and they don't typically come with much assignment, or it's not an assignment-oriented class. It's more about learning a few different things. One of the seminars is integration with practitioners. We have local engineering firms come in, so you get to meet with them, you get to network with engineers in the area and learn about what's important in Seattle. And another seminar that we have is focusing on, well, you spend a lot of time learning theoretical aspects in the classes. How about approximate methods to get quick ballpark answers? That's something that's very important for structural engineering. So we have a seminar on that as well. We also have a seminar that's focused on research projects. So we'll introduce several research projects. So beyond those general requirements, whether you take the thesis or the non-thesis will dictate which of these 2 boxes you're in below that. If you're in the non-thesis, you would take 15 coursework credits. That's approximately 5 classes, typically 3 credits per class. And these can be also graduate structural engineering mechanics courses. We have a few approved undergraduate courses that we feel are advanced enough, and additionally electives outside of structural engineering mechanics, and I'll list several of those. If you're on the thesis side, instead of taking 15 credits, you would take 6 credits of coursework and 9 credits of thesis. And likewise, those coursework credits can be from our graduate courses or courses outside of our department. And you can transfer up to 6 credits from another program or another university toward these degrees. Those credits cannot have been used to get your undergraduate degree, however. They have to have been credits that were above and beyond the requirements for your undergraduate degree. And of course, they have to be comparable to our graduate credit technical level. Okay, so PhD requirements, if you're thinking of doing a PhD. So here's some of the requirements that are listed. You need a master's as well, and this is very often taken on along the way toward the PhD. So students will apply here thinking they want to do a PhD, they'll get a master's along the way. After you get the master's, you would do a PhD qualifying exam. This is a written exam. Sometimes one of the scary parts of getting a PhD is going through this sort of exam, but the students we get do well. We want them to do well. Then after the qualifying exam, you'd have to take additional coursework beyond the coursework I've already listed for the master's. The general exam, which is where you present to your dissertation committee what you plan to do for your research. And then, of course, the final dissertation you have to put together and defend that, the final examination. Typically, this takes 5 years, and that will include a master's in science. I should say maybe 5.5 years, typically, to complete the PhD. As an unofficial first requirement when you get here as a master's student is finding a research project. And I think I may get to that. Apologies for jumping back and forth. I may get to that a little bit later. And in case I don't, finding a research project, we'll bring in our thesis-based master's students, and will be offered a research assistantship or a TA. And the plan is that you will work as a teaching assistant. And while you're here as a teaching assistant, you will interact with faculty and select a research project. That doesn't mean you cannot, even before you get here, interact with us and try to settle on a research project before getting here. We have that happen every year as well. For example, this past summer, one of our students who was only supposed to start in fall was already down in the lab getting a stipend, working on his lab aspect of his thesis. So you can absolutely get a head start on that. And having said that, some don't know which project they want. So they get here, they would prefer to have a TA and learn kind of the lay of the land and what faculty are working on which particular project. So I won't go into too many details here, but if you go online, you can get a little, you can look up our program plan. This is something you'd fill out in your first quarter when you got here. So you can fill out the 4 quarters in the first year, 4 quarters in the second year. you could use this to estimate some kind of timelines for how quickly you might finish. You'll also see this online. It's more kind of a few more details beyond what I've mentioned above. What I mentioned above is pretty much everything, but here's all the very kind of explicit details, 39 credits of coursework and 3 credits of seminar, potentially if you like, and so on. So those are online if you want to see them. One thing that I often get asked is, how long does it take to finish? 42 credits is what we require overall, so that would be 14 credits per quarter if you wanted to finish in 3 quarters. So that's really tough, but it does get done. It is a lot easier if you do have some credits to transfer. That can make it a lot more approachable. So we have a lot of students who do finish in 3 quarters, but almost inevitably they have some credits to transfer. 4 quarters is a lot more common. And this is also common because even some students that might be able to finish in time want to take some wraparound classes. That means some classes they did not have the prereqs for when they got here, but they would in their second year. For example, Earthquake 2. It's offered in the fall. You're not allowed to take it when you get here right away, but in your second year, you would be allowed to take that. 5 quarters is also very common. That is a little bit of an easier path, but of course it takes a little longer. More than 5 quarters is also very common for students taking this part-time if they're working at the same time. Also, a lot of students take internships in the summer, and many of them end up working at the same place full-time after they graduate. So we do offer some classes in summer, but a lot of students actually end up working instead of taking classes in summer. If you look online, you'll also see a list of some of the civil engineering electives. I'll talk more about the kind of the most common ones that students take. But if you look online, you will see this sheet as well that will list a few more. Note the number, the CEE number is actually out of date, but the names of the courses are identical. So if you find a course based on the title of the course you like it, we will still have that course. Okay, so what do we offer in our program? We have, we sort of divide it in two, and then the boundary line between these two aspects isn't always obvious, but we offer a good selection of analysis courses and design courses. So these 3 classes right here, if you're seeing it, are 3 required classes. And I've got a little typo there. It says 6 credits, 3 credits, 3 credits. That's actually changed. That's 4, 4, 4 now. They're all 4 credits. So these are our required core. These are the classes we think are the fundamental underlying mechanics that every structural engineer should, every master's structural engineer should. So the first one, structural mechanics, I'm actually teaching this class right now, focuses on really augmenting and filling in your class that you may have had on structural analysis as an undergraduate. So this focuses on the stiffness method, both direct analysis and variational or integral formulations of it. So it's very likely you've heard terms like virtual work. We'll spend a fair bit of time making that actually make sense. We teach it to undergrads. Most of the time they don't get it because it's hard. It's a really hard topic. We need to spend time talking about it. It's a very powerful tool, a very powerful analysis tool, and we'll spend a fair bit of time on that. Then we do beams, trusses, frames. We actually do 3D frames. So think of a 50-story 3D moment frame. We do that. That's something we often don't teach in undergraduate classes, but we build up the machinery needed to do that sort of analysis. And the machinery you need to make your own structural analysis code to run those kinds of analyses. We also do a lot of buckling, not just Euler-Bernoulli beam buckling, but buckling of systems as a whole. And lastly, it's sort of the driver's license you need to take the later classes. We spend a good bit of time on integral methods, which are sort of a welcome to graduate school topic. And this is a 4-credit class. And the next class is structural dynamics. It pretty much takes 501 and adds mass times acceleration to Newton's second law. So it's not just statics anymore, but dynamics. We do a lot of discrete, so multi-floor structures where we model them as discrete systems, but additionally continuous. So modeling the vibrations of beams, modeling the vibrations of beam columns, both time and frequency domain analysis. There's a fair bit of writing your own numerical analysis codes for nonlinear problems. That's taught by Professor Calvi. And then the last core class is CESG 504, finite element methods. Finite element methods is sort of the sledgehammer we can use to solve any problem, but it requires a lot of foresight to be able to make sure the answer you get is actually a reasonable answer. It will always give you an answer, whether it's a good answer. Requires you to take a class like this. So if there's a few pictures there, instead of modeling stick structures like beams, columns, trusses, what about 3D blobs of material? For example, on the bottom and the middle, column, girder system connection. That's not a simple beam column connection. That's sort of the analysis we need to run there is a really complicated interaction of normal stresses and shear stresses, finite element methods to be able to solve those kinds of problems. Analysis electives, so these classes are things you can take. Engineering computing, this class is getting more popular every year. A big part of that is Professor McKenzie, who teaches it, is a structural engineer who knows a heck of a lot about computing. So you're going to learn how to do a lot of IT-related topics from a structural engineer. You'll learn a heck of a lot in this class. It's focused on Python, which is also a valuable tool even outside of, particularly within structural engineering. It's beyond, it goes well beyond the STAR field. Nonlinear analysis. Typically, we don't teach too much nonlinear structural analysis in undergraduate programs because it's just really hard. The behavior of structures after they yield, the behavior of structures when the deformations get large. So that's what the two kind of aspects that you'll get into in this class. So geometric nonlinearities and material nonlinearities. Structural stability. Additionally, we like to solve equilibrium solutions. This class focuses on the second part of that is whether those equilibrium solutions are stable or not. So solving equilibrium doesn't do us much good if we don't know whether that equilibrium is stable. A big part of this class is also analyzing nonlinear behavior of structures. So we look at structures, how they behave before buckling, after buckling, inelastic buckling as well, lateral torsional buckling. A lot of these really kind of important instabilities that we have in structures. Elasticity, and I should say 507.1 and 2 are offered every other year. So this year it's 507.1. Next year when you're arriving, it will be 507.2, which is elasticity. So this is why also some students like to wrap around so they can take both of these classes. So 507.2 focuses on, I talked about the value of finite element methods. This is the class that tries to solve some of those problems analytically rather than using numerical methods to solve them. And at the very least, we provide the fundamental basis for finite element methods. So instead of, again, solving stick structures, we solve forces and stresses on arbitrary blobs of material. ESG 508, materials modeling, this focuses on, well, now that we know the stresses and deformations of our structure, is it going to fail? Is it going to creep? Are we going to have relaxation and several other sort of end states of our structure? 509, reliability and design. The word design is in there. I've still kept this on the analysis side because a big part of this class is learning about probability theory and applying it to structures. Structural engineering is moving more toward a probabilistic approach and away from a deterministic approach. The loads we have on our structures are not deterministic. There's a great deal of variability in the loads, so we should start analyzing our structure with that in mind, and analyzing the factors of safety that we have with that in mind. Okay, on to the design electives. And we're going to have the ones you think of, advanced reinforced concrete. So analyzing more complex reinforced concrete structures than you might kind of be used to from an undergraduate class where you may have focused on beams and columns. So here, shear walls, a little bit on two-way slabs and things like that. Pre-stressed concrete design, this is taught by Professor Stanton. So he's got years of experience in pre-stressed concrete. This is a very popular class, I should say. Advanced structural systems. So you learn a lot about individual structural components. This class tries to put that together. Particularly, we talk about lateral load versus gravity load systems. And additionally, because they're quite important, this class spends a fair bit of time on two-way slabs. Advanced steel design. This class is taught by Professor Berman. So like the reinforced concrete design, but learn a lot of the advanced topics in steel structures. So bracing systems, post-buckling, dealing with gusset plates, a lot of these sort of complex aspects of designing steel structures, especially in seismic regions. Earthquake Engineering 1, this takes structural dynamics and puts it into the context of how do we design things for, rather than sine function inputs, what if we have earthquake force, earthquake loading on our structures? How do we design structures like this? This class focuses more on the fundamentals of earthquake engineering. Second one, Earthquake 2, will push you heavily into actually analyzing the behavior using software, especially OpenSeas. So you learn a lot about complex nonlinear behaviors and applying it using OpenSeas to performance-based engineering in seismic regions. So this is also a very popular project-oriented class to design real structures in earthquake regions. Wind engineering is another popular class. So Dorothy Reed is actually in our construction program, but her background is in structural engineering. So this will focus on wind loading on structures. I'd forgotten I'd had this slide in here. So we do have something on the seminars. So we have some department-wide seminars that are visiting experts from different places around the country and around the world to give interesting talks. But we also, in the bottom left, have our structural engineering practice talks. I talked about those seminars, I should say. And on the right, our research-oriented seminars. So to give you a sense, this slide, they're just numbers. You're not going to remember these course numbers, but if you're thinking about which courses to take and you're thinking about coming to the University of Washington, this might be a good slide to hold on one side to see what did they offer last year, and it will probably be pretty similar in the upcoming. So this tells you what we offered in the autumn, which was my class, engineering computing, 509, which is reliability, 521, which is concrete, for example, and you can look what we typically offer in each quarter. And then beyond that, we really encourage our students, actually require you to take at least one course outside of kind of our subset of structural engineering classes. We'd like you to broaden your perspectives a little bit. So taking classes from construction, about energy in the environment, geotechnical, hydrodynamics, geohazards, especially if you like seismic geohazards, is a great one. But we really like you to get some courses from outside. We also like it and are happy to have our students take classes from mechanical engineering. Here's a list of a few that you may want to look up. Fracture mechanics is a great one. Composites is another great one in aerospace, material science. So we have a lot of students taking classes here. And as I'd mentioned, a lot of my students, my research is in aerospace. So I frequently have students take 3 or 4 classes from outside departments. Also from architecture, construction management, a lot of our students actually take construction law. They plan to be in project management. Applied math, I like to say you can never have too much mathematics. So we also have a lot of students taking classes here, improve their foundation so they can do a lot of structural analysis. Here's a short list, switching gears a little bit here. If you're thinking of doing a thesis, in that first quarter I had mentioned, we're going to be doing a lot of TA shifts. Here's some of the courses that we typically have our incoming students work on as TAs in their first quarter. So mechanics and materials, intro to structural analysis, steel design, reinforced concrete design, timber design, structural analysis. These are all classes you probably had as an undergraduate, and you would be qualified to work as a TA. Okay, switching gears again on to research. What are some of the things we're doing, especially if you're interested in a thesis-based master's degree? So in the top right, this is something we're really excited about. I had mentioned Professor Berman is doing natural hazard reconnaissance. So this is a brand new center we have. So you fly to a location where there's been a disaster, like the hurricane that we just had in Florida. They fly several drones with advanced sensing equipment above it, assess the current state. This doesn't just inform kind of future design code aspects. It also helps even first responders and structural engineers who plan to walk around and do forensic analysis afterward, where they should be going, what they should be focusing on. So we've got an army of drones here. We send them out whenever there's a disaster to go fly and assess situations. We've got a lot of research in the top left on seismic structural systems. That picture in the top left is actually a concentrically braced steel frame. You can see the two braces at diagonals, and see the portal frame around that. So we have a lot of, our lab is, you might think it's kind of small, but it's really active. We have a ton of research going, active structural engineering, seismic research going on. Other research efforts we have going on right now, and especially relevant to the Pacific Northwest, is induction zone earthquakes. We're learning a lot from our colleagues in geotechnical engineering and in seismology about the hazard that we live with here in Seattle. Things we didn't know even 10, 20 years ago, that we might get hit with a significantly larger magnitude 9 earthquake than we had anticipated. So we're trying to catch up. Folks like Professor Eberhard in our department are trying to assess what buildings in the inventory of structures in Seattle, in the Seattle area, are delinquent. How can we improve the safety of this area as quickly as possible? Innovative timber systems, also very relevant in the Pacific Northwest. There on the bottom right, that's an actual 2-story timber structure with a rocking wall lateral system that one of our students went to test on a large scale shake table in San Diego. So we have a lot of renewable timber. We have a lot of opportunity to improve our construction using timber. So we're doing a lot of research on the behavior of timber structures in earthquakes. We also have a great deal of research on rapid bridge construction. So putting bridges together really quickly with precast reinforced concrete and pre-stressed concrete segments. So this includes both lab testing, as you can see in photographs here, and also a lot of analysis. We've had a number of students work on this project over the last decade. I've mentioned Professor Lehman is also doing a great deal of work on concrete steel composite structures, so concrete filled tubes and things like that. This research is also still ongoing. Professor Motley, I talked about doing tsunami loading on bridges and other civil engineering structures. I always really like to show this one because this is a simulation of a tsunami coming in, contacting a bridge. So his analysis is about turning that into loads we can put into the design code. Right now, this is a brand new thing. We didn't know we would have to put these loads into our design code. So we're starting to realize we're going to have to sort of change the way we analyze and design our structures in coastal areas. I'd mentioned Professor Calvi has this brand new panel tester. You can see a specimen in there. So this is a specimen that could be a representative specimen within a larger structure. And we can apply any stress state we want on there and really get to the bottom of the behavior of reinforced concrete structures, of aerospace structures. In fact, we're placing segments of aircraft fuselage components into here and applying stress states we anticipate in real scenarios and seeing how we can learn more and change the way we design, improve the way we design systems. This is another really exciting facility we have. We are X-ray scanning facility, so we can look inside structures, we can assess cracks, fracture, damage without breaking them apart. So this is a really valuable tool. Structural vibrations laboratory, this is mine. This is kind of unique within civil engineering departments. Civil engineering dynamics typically focuses on the vibrations, better say the dynamics of large structures and earthquakes. But especially being in aerospace focused, I'm more interested in smaller structures and higher frequency vibrations and large deformations. So this is a little bit different than you'd see in many other departments. We have a fatigue testing shaker on the bottom left in the picture. But I also do small scale earthquake simulation or earthquake experiments on here. Again, the post-disaster research facility, I talked about that a few times. We have a large-scale structures laboratory. I mentioned this one before. We have all sorts of full-scale structural components. We don't have entire structures in there, but we have portal frames, brace frames, things like that that we can test in. Structural creep testing laboratory. This is a new addition as well. We can test the creep of structures over kind of persistent loading over time. Okay, and if you have questions about any of those research topics, feel free to reach out to our coordinators.
Yeah.
So feel free to reach out there, or just look up the faculty and reach out to us. And we'd be happy to give you far more details. We usually talk more than we should when you ask us about research. So we'd be happy to talk more about that. Okay, so summarizing some of the things, why UW? We have an active and diverse research program, just anecdotally, coming from research in sort of the aerospace realm for a few years. I couldn't be happier to be back in a civil department. Just seeing the way the folks in this department, the researchers in this department, think about mechanics, think about physics, mathematics, and structures broadly beyond civil structures and within civil engineering is really inspiring. And I think we do a lot of great broad research topic structures. We have research funding from Departments of Transportation, Sound Transit, Federal Highways, National Science Foundation, Pacific Earthquake Engineering Research from United States Air Force. We have a lot of international engagements on earthquake engineering. Recently, especially, we're getting a lot of connections to Japan and Italy and doing structural engineering seismic analysis. We have a few visitors here right now collaborating with us in these areas. Despite what I think is a good research program, despite all the time we put into that, I'm also inspired by how much my colleagues love teaching. So you'll find the structural engineering group we've had within civil engineering have had 2 professors get the distinguished teaching award, and both of them were within the structural engineering group. So we love teaching. We love showing everybody just how excited we are about things we can do in structural engineering and mechanics. Really well connected with local industry. I've got a slide later where I talk about where our students go, and a big part of that is because our faculty are really well acquainted with the engineering companies around the area, and our coordinators are fantastic at setting up career fairs and things like this to get you networking opportunities with practitioners in the area. Seattle's also booming. If you are from Seattle, you know how many cranes there are in Seattle. If you visit, you'll be inspired, I think, by just how much construction activity is going on in the Seattle Puget Sound area. So we're ranking really high in terms of the number of civil engineers employed per 1,000 people, number 2 in the country. So sectors, this goes beyond just structural engineering. This is the construction sector, but the anticipation is there will be almost 220,000 jobs in construction by 2020. So there's going to be a lot of opportunities to find jobs in this area. That's not to say that all of our students end up here. Lots of them will go to California, Chicago, and other places in the country to do structural engineering as well. Now, specifically within engineering, the number of positions per year is, notice that, 650. I said our program has 45 students. So our students get hired really quickly. They get snapped up really quickly by the local companies looking for really good structural engineers, and they've come to learn that we produce good structural engineers, and they hire our people. Where do our students go? As I said, many of our students end up as interns in their first summer, and nearly all of them take full-time jobs in the place they were looking after graduating. I say nearly. I would like to say all, but I haven't met and chatted with every single one of them, so I would feel that's not entirely honest. But I typically advise 5 to 10 students per year for their course selection advising. And in my 4 years here, all 25 or so students I've advised have full-time jobs, the jobs that they wanted in the place that they wanted. So again, we do really well. The local firms know us. Firms around the West Coast know us. So our students have a really good placement rate. Very competitive companies like MKA, KPFF, CPL, a lot of fantastic sort of advanced structural engineering firms that are housed in Seattle. And I had that little picture on the bottom of the Amazon spheres, if you've heard of these. Even if you haven't, it's just a really cool structure. And I put this in there because one of our graduates came back to UW to give a seminar on designing that structure. So he worked at, I'm gonna get it wrong, I think it's MKA. And he came and was talking about how being in the design meetings where they were trying to design the structure along with the architect that you see in the bottom and the middle. And I just think that's really cool. You get to be on exciting projects like that. Another one of our students just came back to visit Seattle. She's had been in Chicago working on the Vista Tower there on the right. So this is a multi-story, high-rise, really exciting structure to work on. So if you want to do interesting things as a structural engineer, our students do a lot of really, really interesting work after they graduate. Beyond civil engineering structures, mechanics is broadly applicable. My students have been hired at Boeing, Aerospace Research Corporation, drone startups. We have a lot of students get hired by departments of transportation and other government research labs. And another thing I haven't focused on as much just yet, but of course, PhD, academia, and other government research labs is another avenue that we have a lot of students going to as well. And lastly, I think my colleague that did this last year liked to say, Seattle's not a bad place to spend a year and a half. I think that photograph doesn't even quite do the real thing justice if you see it on a nice night like that photograph was taken. It's a really beautiful place. There's a lot of fun stuff to do here. And I'm not going to say it's entirely affordable, but it's affordable enough. And the views and the lifestyle and being in Seattle is really enjoyable. So having said all those things, I would be happy to take questions.
Yeah, so if you have questions, please open the chat, which you can do on the bottom, and feel free to put them in the group chat.
I have a quick question. So you mentioned that you can get 6 credits from your undergrad.
Do you know what the acceptance ratio is for international applicants?
That's a very good question. I don't. Unfortunately, that is a number we couldn't find.
Yeah, it's a good chunk of our students are international students. You know, knowing how many apply versus how many are accepted, I don't know offhand, but it's a pretty reasonable chunk.
And while we're waiting for questions, I would add, when I was a graduate student, I visited Seattle on a vacation. And when I went back to school, my thesis advisor said, "So where do you want to end up?" And you know, after visiting Seattle, I told them, "Seattle, there's no other place I want to be. It's just such a beautiful place." So, you know, I don't know how I got lucky enough that there was actually a position when I graduated. I feel both privileged and just really, really happy to end up in such a nice place.
We can hang around for a few minutes as questions kind of come in, but if there, oh, here we go. Here we got a couple more. They have a question about transferring the 6 credits from undergrad. Is there a specific form or additional requirement? Essentially, the way that works, I can speak to that, is once you are accepted and enroll here, you'll just work with some of the grad advising and the team to really do work on analyzing your transcript to make sure that it didn't count towards your undergraduate degree. Usually it just takes a little bit of back and forth with your undergraduate institution. And we work with the graduate school, which kind of oversees all our grad programs here at the university, to get those transferred in. So it usually takes a little bit of time, but as long as you know that coming in and get that process started early, it's usually not a problem. As more questions come up too, you know, maybe you don't have a ton right now, feel free to always email kind of the general info in email. It's ceginfo@uw.edu, and that's managed by all the advisors. And so we can always respond to your questions or pass them along to faculty.
I do have a quick question.
Somebody is asking if once you earn your master's, is it possible to continue on to a PhD? And can you talk maybe about what that process could look like?
Yeah, absolutely. So we have a lot of students that come here not knowing for sure whether they want to do a PhD or not.
In
In
fact,
fact, we've had
the majority of students
that continue to do a PhD when they first got here probably were not entirely sure. And oftentimes we find
I would like, but I want to learn a little bit more about research first. So we completely understand that. We have a lot of students who've told us that they're thinking about doing it, but they want to learn more from the master's first. So we don't hold that against students in any way at all. We understand when we bring somebody in, the master's is what we initially bring them in for. And at any point during their master's, as they go through that 2 years to finish their master's, that conversation typically starts out pretty naturally. Yeah, this is going really well. I really like it. And there's a fit with the advisor, and the student will stick around for a PhD. So that's, I would say, the more common route than that comes in immediately knowing what they want to do a PhD. And on the other hand, we have students coming in saying, there's nothing else I want in life, I want to do a PhD. They start doing master's research and they say, you know what, maybe not. I'd rather just go work and finish my master's together. So both ways we see both of them.
Kind of along those lines, if you're interested in applying directly to the PhD program, do you encourage them to reach out to advisors before applying, and what do you think is the best way to kind of make use of that time?
Yeah, I think reaching out to, especially really sure you want to do a thesis and you want to do research, I would say that reaching out to an advisor is a good idea.
And I would say not the line, I would say your decision for doing that is less that you want to do a PhD and more that you're just really sure you want to do a thesis. You want to do research. And you know, that will very likely lead into a PhD, but if you really want to do research, reach out, whether it's a master's or a PhD. I would say that would be the way to go.
Any final questions out there? Okay, well, thank you for joining us. Again, if you have questions, don't hesitate to reach out to us, and hope you have a great rest of your evening.
Thank you.